Hey everybody, Dr. A here, and in this video we're going to be exploring an example dealing with distributed loading. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
Okay, in this example, we're given a uniformly loaded member with a length L, and we're being asked to show that the equivalent load is always located at L over 2. Okay, so let's take a look at this. Let's say that we have, this is still given information, by the way. Let's say that we have this member, and it has a length L, okay? And we're going to go ahead and kind of put on some axes here, W and X. And I'm going to give us a uniform load. Uniform load W, okay? And so, again, this is all given information, and we're being asked to show that the equivalent load, capital F, is always located at L over 2 from an origin. So let's go ahead and look at this solution, okay? So our centroid calculation is x bar, and that equals integral from 0 to L, x times w as a function of x, dx, all divided by integral 0 to L, w as a function of x. So please be very careful. Notice that we have w as a function of x, but in this numerator integral, it's x multiplied by w as a function of x. So don't get confused and think it's x times w times x, okay? This right here is function notation, okay? Just make a note of that just in case it wasn't clear before. So in this particular illustration, we're going to have integral from 0 to L x times w, because our load function is just, it's a constant, it's a uniform load, right? Uniformly loaded, so w is just constant. And then, let's see, we got x times w times dx over integral from 0 to L w dx. So remember, we shouldn't try to cancel anything right now, although we kind of could because w is a constant. So we'll make a note here. W is constant in this case. So technically, in this particular case, you could cancel the w's because it's constant, okay? I know I emphasized in the last video, don't just cancel things in the integrals because they're functions, but in this case, it's a constant function. So I'm not going to cancel it, though, even though we could, but I'm not going to right now, just so I'm consistent with what I said in the previous video. So let's go ahead and crank these integrals through. So let's look at the numerator integral. We have an integral with respect to the variable x. So we're going to end up with wx squared over 2 evaluated from 0 to L. That's my numerator. My denominator is going to be wx evaluated from 0 to L. All right. So now the integrals have been evaluated. If you want to now, you can reemphasize w as a constant in this example, so we can cancel the w's here. And now we need to evaluate these integrals. So we're going to get L squared over 2 minus 0 squared over 2, of course, and then divided by L minus 0. So what do we end up with here? We get L squared over 2 divided by L. So doing some very basic algebra here, we get L squared over 2L. And then sure enough, we're left with L over 2. And there you go. There's your L over 2. So what that is telling us is that our equivalent system looks a lot like this. We have our force here equal to WL, and then it is located at the exact middle of that load distribution. So this gives us the following conclusion. for uniformly distributed loads, the centroid is always at the midpoint of the length over which the load is distributed. It's at the halfway point, L over 2. And there you go.